And I thank the organizers for having the opportunity to have this presentation. So my title is slightly different, but we speak about the same things. Where's the... Ah, here it is. I would like to thank my different collaborators in the course of the years that this has been prepared. Dr. Alexandre Faure, who is a homonym of Frederick Faure here, Professor Wiggins, Professor Roberts, and Professor Cooperman. So, as you see from this line, I'm busy with molecular astrophysics now, and the people there ask mainly questions about scattering problems. Molecular astrophysics means that you have a cloud of molecules which are far apart, that you never have three-body collisions, so that the idea of isolated bodies reacting one by one is a very good one. So it's a very good test ground for all the ideas that have been developed here in general in these conferences, where we never or nearly never take into account the medium, the dissipation that can be induced by solvents and all these things. So let me begin properly. And I will come back to this as the speech goes on. What is a transition state? A transition state, and we'll speak about Hamiltonian classical dynamics as a kind of a continuation of the preceding talk, since the ideas will be somewhat similar, albeit but extended to many more dimensions. So a transition state is a very old concept, dating from the 30s at least. It's the idea that between a stable or metastable state A and a stable or metastable state B, whatever this means, it may be in solid state physics, maybe in molecular physics, maybe in nuclear physics, there is something in between which is unstable and decays either that direction or that directions. And this idea, very simple, is immediately translated into some very, very simple picture that is around also, as I said, for 70 years maybe. So if we call psi some coordinate that describes the course of events from state A to B or from B to A, here or there, if I have a Hamiltonian function that looks like kinetic energy plus potential energy in one degree of freedom, you have something like that. That means you have some stable or metastable, you name it quantum mechanically or classically, it's the same. Same thing here. And you have to jump over this barrier to get from there to there. And since we are at a given energy here, we go back and forth in this idea. So if we want really to jump from here to there, we should add some dissipation. But here, if I'm there, I'm going from minus infinity, go over the barrier here, and go to the other side at plus infinity. These very, very simple ideas are translated here in phase space. If I put a zero of energy here, you see that if I'm above zero, I can go from left to right or from right to left on the green lines. If I'm below the threshold, we call this the threshold. On the blue line, I stayed here forever. And if I'm just at threshold, I have several possibilities. Either I'm there, stuck at the unstable equilibrium, or I can travel on the stable or unstable manifolds of these unstable equilibrium points. So this is the very simple setting we begin with. And we shall slowly, as I go here further, complicate this very simple image towards adding more dimensions and nonlinearities. So, as I said, this is a 1 degree of freedom system here, T plus V, I just described. Now, let's go to more than 1 degree of freedom. Very general. The Hamiltonian I shall be speaking about, I say nothing about how it looks like with respect to kinetic and potential energy. It can be very general here. Just a Hamiltonian function. And I suppose that P, my point which I'm looking at, is an equilibrium position, and I put the origin of energies there and the origin of coordinates there, just for convenience. Now, in order to describe things with the hands and to give you an idea what's going on, it's better to go first to describe in detail what's going on with the linearized motion around P. Okay, I will describe a little bit how we go from there to there in a second. Let us suppose that I'm just interested in the linear motion, so I don't forget about this for 1 second. What the Hamiltonian I'm interested at, looks like this. I have two sectors, the black one and the red one. The red sector is about this one. You see here kinetic energy, potential energy, and this looks like an anti-oscillator. That means in the red sector, as I will show in a second, you have V of psi, something like that. Now, the other part, what we call the bar sector, are a collection of harmonic oscillators. And in order to simplify things, I suppose that whether or not there are resonances, I don't care. So the other part will be oscillators. That is, I have this with a direct product of n times, n minus 1 times, sorry. So this is my general setting for transition state. And these ideas also have been known in physical chemistry for many years. So now I'm inventing nothing. To give you an idea how it looks in the configuration space for 3 degrees of freedom, that means n equals 3 here. I have 2 harmonic oscillator, 1 harmonic anti-oscillator. Here's what it looks like. So this is my configuration, my configuration space. You see here the psi, Q1 and Q2 coordinates. I depict here my surface at H equals the energy at my disposal. So in 3 degrees of freedom configuration space, this makes a 2-dimensional manifold, which is, as a matter of fact, a hyperboloid, I guess you pronounce it this way. With here the smallest part that connects that to there. If you were to make an integral of the flux going this way or that way, this would be the minimum. Of course, the total flux is conserved. But if you only insist on going this way, this would be the minimum of flux. So this is very general ideas. Okay. So now, I'm sorry. Oh, why? There's no why. But I insist on that. Okay. In order to define everything that I will speak about, if I don't have that, dynamics is way more complicated.
Right. I was just wondering if you can do this sort of thing for other stuff.
Okay. Maybe later on I will come back. It's an interesting question. I will come back later on when we speak about how to get this. Okay. So always in this 2 degrees of freedom now. So this is slightly simpler than what I just gave. Also to give you a flavor of what's going on. Well, this is elementary, of course. So this is E, the region authorized. So you have here phase space, configuration space, sorry, psi, and one of the bars coordinates here. This region is forbidden, since my energy is negative. Here's my origin, the unstable point. And then trajectories can, of course, be only non-reactive. That means they remain forever, either on the right-hand side or the left-hand side. I added here a trajectory at E equals 0, originated from here, which goes straight away here. This is one of the stable and unstable manifolds. And then, if you wish, we can continue to positive energies, and then you have 3 categories of trajectories. The same as before. It's not because you are above threshold that you must react. You can stay here, like here, the dash dot lines here. You may react, like the black one that can go on this way or that way. Sorry. And then there's a third category of trajectory, which is this one. That stays here forever, which is periodic orbit dividing surface that was alluded to by Kevin Mitchell just before me, which divides this part from that part. I recall you that this whole setting is linear. We are still linear here. So everything is very simple in the linear size. So, to answer your question and to see how we arrive at that, in order to see what's going on, linearly, if we begin with a general Hamiltonian, of course, as you all know, we must go through the linearized dynamics. So if I make x, which is any of the coordinates in the phase space, so let x be any of the p, q, pi, qi, p psi, or xi. And if you want to study this, that means d of delta and delta x is equal to x minus x of the equilibrium point. So you want to know how do these quantities evolve in time. This is derived from the Hessian of the Hamiltonian, this being the symplectic matrix taken at the equilibrium point. So this is this equation. This is a set of numbers that tells you how do the linearized dynamics look like when you are nearby the equilibrium point. So there, general theorems tells you that you have several possibilities, for the eigenvalues of M. You can have, firstly, imaginary eigenvalues that go by pair. You can have real eigenvalue that go by pair. You can have zero eigenvalue. And you can have also what are called loxodromic eigenvalue, which are these type that go by 4. And in order for us to treat a transition state, we must have the following structure of the eigenvalue. So we must have for n minus 1 eigenvalue this structure, that means the bars, and for the last one, this structure, meaning the transition. So this sector will be the stable sector, or the elliptic sector, let's say, and this sector will be the hyperbolic sector. In order to have a properly defined transition state, this is the situation. I do not, the situation today. I do not claim that this, all the stories there, that's what we know today.
It just says zero eigenvalues. There are no zero eigenvalues.
We'll discuss about zero eigenvalues in a second. This I will not discuss because I don't know what happens if I have that. Zero eigenvalues come in 5, 6 transparencies. Okay, so when I begin with my general Hamiltonian, know that I have an equilibrium point and that the structure of eigenvalues is a green-red here. I know that if I linearize, I end up with this Hamiltonian, with kappa and omega I being the relevant eigenvalues, which is exactly what I spoke about beforehand. Now, what is great in the linearized regime here is that this green sector, I can allow for exchanges between the different oscillators in the green sector. I don't insist on anything about the dynamics in the green sector. But I insist on having no exchange between the green and the red sector. So my green sector here is invariant with respect to that. That is, what does I mean? Suppose that for some reason, psi equals peak psi equals 0 as an initial condition. Then equation of motion show that psi dot equals peak psi dot equals 0. That means if this is 0, this remains 0. That means that the flow will be constrained on this part here, on this equation here. We call this a normally hyperbolic invariant manifold, which is some big word for something not so complicated. Normally hyperbolic invariant manifold, and I don't know who first proposed this. Up to me it's Wiggins, but I'm not sure about that.
I mean, it's obvious that this thing should be block diagonal, or it could be.
No. What I say, I insist on that. This is a condition. Then I have that. Of course, we'll see later on. If you have a potential surface Hamiltonian, you look at the equilibrium point where the gradients of the you can have anything. Okay. But in order to have that, no. If you have that, you have that. I don't know the other way around. If you have that, you have that. What does it mean? It's an invariant manifold for the flow, since if I'm inside there, I stay forever. And if I go away from there, I have two properties. It's hyperbolic, as the red part shows you, and it's normal, because since this object is made of trajectories, no trajectory in the psi sector can be tangent to this one, so it's normally hyperbolic. So these two properties are of importance. Let's go further on with the properties of this green object. It's a sphere, as you see here. It's a 2n minus 1 minus 1 sphere in the 2n phase space. And on each point of this object, as I said, each point here spans the hyperbolic plane. So I have a structure that I will try to show you in more detail of this Hamiltonian. Please note that still I'm very simple thing, but still I'm totally linear now. So all discussion is linear for the moment. Let us begin with the hyperbolic sector. And let us imagine, so linear, 2 degrees of freedom now, because otherwise it's too complicated to draw. So here's the gray thing you forget, I'm sorry. Here's my periodic orbit, which is my normally hyperbolic invariant manifold. Maybe I write down the Hamiltonian there. Just a second to make things easier for you. So it's this thing there with n equal 2. So you see, if n equal 2, this reduces to one oscillator. One orbit of this oscillator is this red line here. And I'm interested in the psi sector. You see here? This is part of the phase space. P and Q are the oscillations coordinates. And as I can't, of course, draw in 4 dimensions, I just draw one of the dimensions, the psi sector, namely psi. I could have written p psi, it would change nothing. And you see that on each point of the periodic orbit, I have a stable manifold here in green, an unstable manifold here in blue. And these objects, okay, are here around. It's difficult a bit to draw, but you can imagine there are 2 kind of crowns surrounding my periodic orbit. That, okay, will come in a second. So this is the easy part. We all know that periodic orbits have stable and unstable manifold. What about the other sector? Still in the linear case. So this is called linear and stable manifolds, hyperbolic sector. Still in the linear regime, I can do things in the other part. Inside, oh, I'm sorry, I didn't say. This is inside my energy level. Now, in order to see what's going on outside my energy, in the stable regime part, I need to go outside my energy level. So here's my equilibrium point. Here is energy. I'm sorry, this is not very well focused. I guess you see it better here. So linear regime, central manifold. Here's energy, 0 here, growing, so I'm above threshold. This coordinates is the vibration coordinates. This is the momentum, and you see here the periodic orbit that I described a second ago. All these periodic orbits here make up a series here that converges to there. These are called, I guess, the Lyapunov orbits. If you are nearby, linear regime, this exists here. And they make up, all of them, what is called the central manifold of this object. That is, the manifold spanned by all this green motion as energy evolves away from this point. So the structure is this way. You have, from this point here, you have an unstable manifold, and here, the stable manifold. Dimensions, here, hyperbolic, the stable manifold is 2, I have n minus 1 variable, so it's 2n minus 2 in full phase space, and the hyperbolic part is 2 in phase space, adding to 2n. So this is a very large object, while the other part is very small. Okay, I try to summarize the whole picture here.
It's not periodic, it's quasi-periodic.
Okay, this is linear, so it's periodic or quasi-periodic. Quasi-periodic, but it's of no importance. Tori. Sufficiently big. Totally foliated by tori. Yeah, some periodic orbits, of course. So here's my point here. From that point, so these are very collective coordinates here. On the vertical axis here, I plot something which looks like the whole central sector, the Q's and P's. Here, in the going to U sector is a psi and peak psi. And here is energy. So it's a condensate of my whole phase space. Here's my point here. This point, at the origin of energy, has a stable and unstable manifold that extends here, and a central manifold that opens up in the QP sector. You see here? This is in plane, this is out of plane. Now, if I go up in energy, at a certain point here, I have here my whole normally hyperbolic invariant manifold, which is here. And normal to that, from that point, away from the QP sector, I have in the psi p psi sector stable and unstable manifold of the normally hyperbolic invariant manifold. So this is the whole structure that will command transport in phase space in a simple way. So this complicated object is the equivalent for more than 2 degrees of freedom of what we are accustomed to in 2 degrees of freedom, which is simple here, a periodic orbit dividing surface with its unstable and stable manifolds. So this object here, which is more complicated, but whose structure is very well understood, replaces what we know about normally in 2 degrees of freedom system. The structure is the same, just we have to add dimensions and be very careful about what we speak about. Yes, I will speak 5 minutes about dimensions, or maybe later on if we ask questions. So, after this linear setting, which is not too complicated, I hope, I will show you that all these objects, okay, we can calculate them. As a matter of fact, I will show you in an example that is relevant, I would say, that all these objects can be calculated and found in true dynamics, nonlinear dynamics. Why is it so? Because what we know from dynamical system theory is that when we go from this linear setting to the full nonlinear setting, in the neighborhood of my fixed point here, I have theorems that guarantees that this structure is tangent to the true structure. What does it mean? It means the following. In the hyperbolic sector, it's very easy. Here's my point. Here is my linearized dynamics. And we know from theorems in dynamical system theory that the nonlinear dynamics will be tangent to this dynamics. And that, moreover, that if I integrate along this line, I can go forever, or as very far, I would say. Well, forever, it means nothing here. There are intersections, homoclinic, heteroclinic intersections everywhere, so it's complicated. But I can go further on. However, in the central manifold sector, the theorems are weaker. I know only that this image here, okay, is true in the neighborhood here, and if you go to the nonlinear regime, it's true only in the neighborhood in time and space. And over there are problems of uniqueness. Well, okay, forget about this here. So, let's go to see this in the nonlinear regime. In order to do so, I will be very specific on the system that our colleagues in astrophysics have interest in. So let's go now back to something more actual. We are interested, as I said in the beginning, in interstellar media, formation of star, environment of young stellar objects. These are media where the density is low, the temperature is medium, between 10 and 300 Kelvin. What is very important is the low density, as I said. And what is also very important is that atomic and molecular hydrogen and helium possibly are the dominant species of all molecules. And as you know, atomic hydrogen, molecular hydrogen, and helium are totally transparent to infrared and visible light. So that it's and also microwave light, of course, because all the three molecules or atoms have no permanent dipole moment. So it's very difficult to observe them. They are the dominant objects, you cannot observe them, so which is quite frustrating. And for long, this fact has been, we went around this fact by looking at the collisions between hydrogen molecules or hydrogen atoms with other polar objects, like here water, CO, CS, CN, simple molecules. And we want to know how does the temperature of H2 or H, that is the kinetic energy of H2 or H, when colliding with those polar molecules, how does this kinetic energy transfer into rotational energy. This is a very old problem that has been treated over and over again. For example, if you put here CO molecule or CS molecule, this is fairly well known. And this was a good point to begin the stories about collisions with non-zero angular momentum. This can be done, of course, quantum mechanically, so maybe later on we can make some comparison. So, in order to look for that, the Hamiltonian for this collision or that collision are very simple in the lab frame. And I consider only for the moment fixed angular momentum direction, not magnitude, but direction. You have here, if R denotes the distance between an H2 and an H2O molecule, kinetic energy of, this is hyperradius, rotation of both molecules, orbital motion of one molecule with respect to another. They turn around, one around the other, which is this L here, and some potential of distance and a collective denomination of the angles. Here down is even simpler for this collision. You have kinetic motion with respect to the hyperradius, rotation of H2O, orbital motion, and some potential. Very simple. Okay, there is a problem there. This is the approximation of this angular momentum. Okay, this is an approximation. As you know, angular momentum motion is very complicated. This is the sphere of an angle of motion of the angular momentum, the three projections of angular momentum on this sphere, where it turns around, and you see that there are two stable, as you know, and one unstable, and we remain here. It's not too bad an approximation, but we know by observation this and this can be observed, and this you never see. So either you have this way or it goes this way, and we stick here. It's too complicated otherwise. So I go back to that. Yeah, put it here. No, yeah. The second one here. And I want to study whether or not I have transition states here that will connect the different states, the channel in and channel out. Who knows? Well, I have here too many things to deal with. I have angular momenta, total angular momentum, radial, and here angular motion, so it's too much. What I would like, there's no reason therefore be any equilibrium point. What I will do is something more, how would I say, something more specific, which is a relative equilibrium. You don't want the whole object to stay still, to stand still. You just want that there is no radial speed nor acceleration, and that the whole body rotates, the composed body rotates as a whole with a constant angular speed and zero angular acceleration. That is like the Earth and the Moon. They do like this. And therefore, what you do is the following. For the eigenvalues of the M, which is down there, under the other backboard there, for the linear dynamics, you want now something different. You want two eigenvalues to be 0, which is angular momentum total conservation, n minus 1 going to, n minus 2 probably here, that are, n minus 2 because it goes from 2 to n minus 1, that are imaginary and 1 real. So you now have three sectors. The total angular momentum sector, where you have a global rotation here with the frequency I told you about, one stable sector, and one hyperbolic or transition sector. And this sector will be transparent for us. We don't look at it, and we will, at the very end, when we'll need cross-sections, we will have to reintroduce this total angular momentum sector. But we shall go into the relative transitions. So just to give you a bit of technicalities, here is H2O, H, and an angle in between, the angle chi, between the dipole of H2O and the direction of the H atom. I'm in the plane here. This one is rotating with respect by theta. This one is rotating by theta H, and this relative rotation one with respect to another. And we derive a Hamiltonian, which is, okay, why not writing it? It's physical Hamiltonian. Just describe you a few terms there. It's just a modal Hamiltonian whose constants are taken from the literature. This is to ensure that the two molecules don't collide with respect to another. It's exponential repulsion. This is the van der Waals potential. Forget about the D's there. This is the van der Waals potential, which is isotropic. And you have two anisotropic potentials. One which is dipole-induced dipole, dipole-induced quadrupole motion potential, and it is known in the literature that these four potentials together make a relatively good model of what's happening at long distances. Of course, at short distances, this is miserable. This looks like this. And I will leave this for the rest of the talk here. Let me explain you a little bit what's going on here, because this explains everything which follows. So, this is the distance here, and you see here in atomic units, this is 4 angstrom about. Here, the angle between hydrogen and water. You see that large distances, everything is flat in this direction and very weakly growing. This is the van der Waals part. A very weak attraction of water with respect to hydrogen here. Here, at short distances, 2 angstrom, 4 atomic units, we have a deep hole, which is the van der Waals complex between hydrogen and water. They stick together. Here, it's a hole, this. In between, because this is a non-zero total angular momentum, this is total angular momentum equal 8 atomic units, you have here this white region, which is the centrifugal barrier. But because this is not isotropic, there is no reason for that to be isotropic. The anisotropy of here is there. You see it here. These terms here. So here, there is a little valley here that separates this part from that part. And this, in the relative, don't forget this is a relative motion, will be our transition state that we shall study. And you see that this is totally nonlinear, because on the one hand, you have all these terms that have nothing to do with linearity, and on the other hand, you have angular momentum in your Hamiltonian. So this is totally nonlinear. And we shall study what's going on in this neighborhood. You can also see in this picture, okay, a few more points on this picture. Here's my equilibrium point I'm looking at. Here are other ones. It's crosses, circles, and stars. Circles are equilibrium points, relative equilibrium points, whose 2 eigenvalues in this plane are imaginary. So stable, stable, stable equilibrium points. This one is stable, unstable. This one, that one, that one, that one. And this one is twice unstable. And you see that since it's not potential plus kinetic energy, this is off-center here, because this is potential energy, this is total Hamiltonian. Well, yes, just for the pleasure of it. Here, if you concentrate on the full line here, you have nothing probably. In atomic energy, in atomic units of energy, as a function of J, here are the energies of those 2 points, this one and that one. And you see that while you increase J, both of them grow parabolically as they should. And here is a saddle node bifurcation that creates them. That means if J is larger than 13 something, the centrifugal barrier is so high that those 2 points have collided, and there's just a wall here preventing anything to enter. And you have the same for the other points, but it's not important. So this shows you where these points come from. The saddle node bifurcation is here. So on this potential, I will do again my story of central, hyperbolic, stable and unstable manifolds. So I recall you before I show you the result. So what does this begin? What does this happen? What happens with this? Well, this linear regime is that in the nonlinear regime. So this is an image of the true central manifold. Here's the point P there. Of that special case, or for some reason it's kind of on over 2 for some canonical transformation that are of no importance here. I'm here in 4-dimensional phase space, 6-dimensional phase space reduced by J equal 8, so 4-dimensional subspace on the full 4-dimensional, the full phase space. Here R, PR, and chi and a half. If I had some plots also with other coordinates, they all look the same. I chose one which is aesthetically satisfying. And you see here my periodic orbits that span my central manifold. Of course, the lines here are just drawn by hand, I mean, by the computer, but by hand, and mean nothing. Normally, you should have a dense set here at all values that surely go from here to there. And I stop here because there, the approximation breaks down. There are some bifurcation, complicated things occur. this idea breaks down at that thing, which is, for the sake of the numbers, 24 centimeters minus 1 above this one. It's above here, about here. We are here about. Here, I cannot go further on. Something else happened. All the ideas break down. Of course, there are bifurcations, which is awaited for. So this is my gray sector here. Let's look now at these objects. Here they are. Also at 24 centimeters minus 1 above threshold. These are the green and red tubes, which are my normally my stable and unstable manifold. Here is my periodic orbit, which is with the normally hyperbolic invariant manifold inside here. Here's a tube of the unstable manifold. Here's a tube of the stable manifold here. All the lines here are made of trajectories. These manifolds are made up of trajectories, so I integrate just equation of motion. And you see here how they go around, going away from here or going towards here and going away this part. And you would have also, if you see here, this is going outwards, going inwards. I've heard the same here. Here, this is part of it. And you say here afterwards, the motion becomes complicated. As a matter of fact, there is here the homoclinic intersection here between this one and that one, and the story we had this morning appears there. Same story going further on, nothing very interesting. But you see here, you go very far away. The tubes flatten out. Here's 100 atomic units. And I can make a projection now onto the asymptotic plane. Okay, before making the projection of the asymptotic plane, something more. Here, I recall that I am rotating at a certain speed. Now, in order to go to the asymptotic plane, the physical plane, in order to calculate cross-sections, capture theory, whatever you mean, I need to go from this abstract space to the true space, because my scattering experiment is done in laboratory frame. So this object, as a matter of fact, I guess it's a green one, is that one, in ordinary space. Here you have, in the lab frame, center of mass lab frame, X and Y, ordinary space. My molecule here is happily rotating in the middle here. Atomic hydrogen is coming here. This is just these trajectories. I put back the angle here that rotates. And it's turning around. So you see that this point here, as a matter of fact, in ordinary space, is some circle here. That means it has to do with Rainbow's effect and this kind of thing. So in order to get there, I have to go there, take into account that there is a phase that is arbitrary, and I can project now these tubes onto the asymptotic plane, which is here. Let's put it this way, probably. Okay, no problem. No, there's a reason, fair. But doesn't have. There is a reason, because this is L, which is the impact parameter that we usually put in the horizontal plane. This is the J, one of the dynamical parameters. So the tubes, when it arrives at infinity, it doesn't look like a tube, but it's a very thin tube here, is here. This is the connection between this object here, my transition state, and the plane at infinity. That means any of those trajectories beginning here in this range will end up here inside. And if I'm outside here, I will never end up here. I will collide with a wall and not enter the inner part. And here, this point here is the unstable manifold, stable manifold, sorry, of this point here. So all is well. Here I can calculate rates and everything, but it's not very, I mean, it's not 2 degrees of freedom, it's 2.5, so okay, it's a bit interesting, but we can go further on that. I have still 10 minutes. So let's go one step further. A step further is now to introduce this Hamiltonian now, the H2O, the full Hamiltonian here. I won't describe you the whole Hamiltonian, it's long, not very interesting. What is interesting is that now that I have one more degree of freedom, which is the JH2, or if you prefer, the phase space is 2 more dimensions, I have more information. I can get more information. So first point, my relative transition state, which is what I described, point P I described beforehand, is this one here. This whole body, the 2 bodies rotate as a whole here. Here's my relative transition state. It looks like this. Why it is like that, I have no idea. That's how it looks like. The van der Waals complex between H2O and H2 is here, this way or that way. But this, the transition state looks like this. The whole body rotates. If you look at the distances and what do I look here? And the value of J, well, for those of you who knows a little bit about that, distances are very, comfortable for an energy here, a few hundred K, that is a few hundred centimeters minus 1, you have 7, 8 atomic units, which is reasonable, what we expect from the physics. We know these kind of things. It shouldn't be a few atomic units, it's not reasonable. 10 or 20 is not of interest. So we are in the right range. Also the J we are looking at are in the right range. Here's L, but J is, there's a 2 J's equals 0 here. So here you see the J, the L's are the order 15 to 20, which is in the right range we need. If it were too small, it would be of no physical importance. If it were too large, not physical importance. It's just about what we need. So this is a physically relevant object. And we can look at the eigenvalues here. You concentrate on the first here, the first image on the top. And you see that the eigenvalues of the linearized regime of this Hamiltonian around the point I just described have one. I just plot one part of the pair because it goes by pair. One real and 2 imaginary eigenvalues here. So it has a characteristic of a transition state. This one is if the H is this way, not that way, but this way. And you see that all are real. So it's totally unstable and you never see it. You never hit this singularity. It's not, it doesn't, well, I don't know what it means for the dynamics. So this is the one of interest. Then to finish, or nearly finish, I would like to show how, in this case, I can see the transition state. So it will be an analog of this image. You remember? I showed you how the normally hyperbolic invariant manifold projects onto the asymptotic plane. Now I have more dimensions, and I can do something more, which is more speaking. So this is it. I'll spend a few minutes explaining this. What are my conditions? What is this? This is a given energy, 300K. This is a plane at infinity, it's asymptotic plane. So I'm far away from my region. I will send off trajectory towards my interaction region. L, the angular momentum, orbital angular momentum is varying from high to 0. Okay? The other two angular momenta, as I said, are 0 at infinity. So these two are 0 at infinity. Then I send off particles. So I need still two more initial conditions, which are the angles. There's no reason for the angle between H2 and H2O here, the two angles here, that's set where I am in H2, H2O. There's no reason for them to be something. So I spend yes, the whole range. Well, for some technical reason, H2 goes from pi½ to 3 pi½, and H2O goes from 2 pi to 0. So you must think of this as a torus. Whereas here, this point is identical to this one, and this one to that one. Okay, as I said, for very large angular momentum, oh, I'm sorry. Black point means I enter and cross my transition state. White point means I don't. So what I did, I integrate trajectories, and as soon as I'm beyond the transition state, I stop and I put a black mark. And of course, as I was lazy, the square is that large. You see the squares. So white means nothing enters the transition state, meaning that I'm so large total angular momentum that my centrifugal potential repels me. Now I'm just below transition state. I see that my transition state is here, pi and pi½ or 3 pi's and a half. Here it is, and you have here the trace, or the shadow, if you wish, of the tubes, which is the border between black and white. Of course, in classical mechanics, in order to have a transition, you must have a stable manifold in between. So the stable manifold is here. This is a trace of the stable manifold of my transitions of my NHIM, to speak properly, here. My transition state is this whole series. As I go down, further above threshold, this threshold, I go above threshold here. This gap here opens. You see here how it opens. Here something, okay, it's maybe still here, maybe not. Something else begins to happen. And if I go far above threshold, which is here, L is very slow. That means I'm far above the centrifugal barrier. Something else happens, chaos, who knows. It's not very interesting. So that means I have three regimes. Above threshold, transition state regime, changing here, and inner collision regime. So if I wish, I can see, even in these very complicated systems with 1, 2, 3, 4 degrees of freedom at least, 4 degrees of freedom, I can have a general picture of what's going on. I begin with H2 and H2O rotating one with respect to another and having this angular momentum one with respect to the other. So 3 angular momenta and this going one. The key point is a relative transition state, which is this object rotating. If I cannot reach this one, I don't reach it, I go away. My first regime. I reach this one at this J star. Either I can escape elastically with an elastic scattering. That means both of those objects keep the angular momentum. I can escape with an inelastic scattering. Some angular momentum is transferred from there to there, or from there to there or there. Then is exchange of angular momenta. Or else, as I showed for hardcore collision, that means I don't care about this. I just zoom across, and I cross the hardcore, this one, on that one. So the 3 regimes here, plus elastic scattering. So just these few images and a little of geometry has shown us that we can say a lot of things on these complicated dynamical systems. And just to give you an idea where we are heading to, you can add to all these coordinates some reaction coordinates, 1 more dimensions. And this will lead to that I will not comment, that will show you that we have a lot of work still to do. These are complicated coordinates that will explain you how to go from this Cn plus x to n plus Cx. That means the reaction coordinates with a complicated transition state here, complicated coordinates. You lose contact with the ordinary world in order to have as simple possible a transition state here in very complicated coordinates, to focus on what is important, where are the tubes, where is the dynamics important, what is stable, what is unstable. You project out from this region towards the asymptotics, and you try to describe your reaction. I thank you very much for your kind attention.
Any questions or comments? I was wondering, I mean, you said at some point, obviously you need an unstable direction.
Yeah.
But you said it's also necessary to have stable direction inside the involving variable.
Yeah. Did I say so? No. You need a stable, unstable region. You need an elliptic and hyperbolic sector, obviously.
If you have an invariant space, which has is unstable and going out of this invariant space, you have never used the fact that this invariant space itself is integral.
No, it need not.
So it could actually be anything.
Yeah. As a matter of fact, I didn't look at for it. In my case, well, okay. If you are sufficiently nearby, okay, one must be careful what one says. If you are sufficiently nearby the equilibrium point, you know that some perturbation theory will tell you that that integrability approximation is very good. That the chaotic region will be very thin. So this is one part of the question.
So there is no equilibrium point. You just have this invariant space. And then
Yeah, okay, if you think of your case, it's different, because your case, if I may have a private discussion here, is that this point here is highly singular, which is different. And then I guess, my guess, that these theorems are different. Do they hold or not? I have no idea. Here's simple, quadratic. Your case is different. There are 2 different cases. Your case or the other way around, when it's non-analytical. This can also happen, that this point is non-analytical, that everything breaks down.
You started out by describing a situation with one state, one unstable direction and all the others being stable. How common is that in molecular problems? Is that usually the case, or
Okay.
do you get distributions of everything? How does it go?
Let me ask you in 2 steps. I will ask you in 2 steps. First step is this one. This case is very general, even if you add angles and dimensions here, because what this means, and maybe I make a drawing. So if I add angular momentum, it's very general for inelastic scattering. Okay. Suppose anything. You suppose here it's slightly attractive, van der Waals, whatever number of dimensions, is always repulsive. How do you say, exponential repulsion. The wave functions don't want to collide. So you have, without angular momentum, it's always this kind of thing. You can have this type. This can be very shallow, of no importance, but in principle, this way. So if you add centrifugal repulsion, you always have this. This is general. And this point here, which is my relative maximum here, has no reason of being uniform over the angle sphere, angle hypersphere. So there will be things like that all the time. That's one answer. On the other hand, if I'm looking for chemical reactions, okay, let's be in detail. Two avenues: Born-Oppenheimer, non-Born-Oppenheimer. If it's non-Born-Oppenheimer, I have nothing to say. If it's Born-Oppenheimer, I guess that, okay, probably topologically this is the most important, either at infinity or in some finite distance. But it's just educated guess. There is a reason for that, but I don't know enough of topology there.
If you have a two-dimensional hill, one is thinking about a barrier between reactants and products, and so it would be some sort of mountain pass.
Yeah, it look, yeah.
It's not going to be a barrier.
Yeah, but I'm not sure about the loxodromy case. There is a problem with loxodromy, so one must be very careful with this kind of thing. It's more than 2, so it's a bit difficult to have in. Same? Okay. Okay. if Colin Verdier says it's that is. Oh, yeah, but I'm not looking this way. I insisted on that. I insist on that.
Effective potential.
Complicated. Yeah. Oh, yeah. Yeah. If you, okay, the only the following interesting case I did not speak because nobody has any idea is when you have something more complicated, when you have branching of those points. When you go this way and there's a branch of reaction, you go this way. This is the next interesting case.
Okay, so let's thank you.